Alright everyone, so let's get to the cream of the crop of stuff where we're gonna look at. But let's just get into it. Alright, so here we have our circuit in front of us. We don't know what this circuit is yet. I haven't revealed the secrets of that just yet. And so we've seen some of these elements before for those of us that are perceptive. We have a multiplexer over here, right? A 4-to-1 multiplexer. We have 4 data lines, one output. So we have a multiplexer. Big whoop, right? We've seen that before. We actually also have a full adder subtractor circuit right here, right? That's another thing we have. Isn't that crazy? The only thing we haven't seen is, well, this circuit in this configuration, right? Well, we have some extra logic elements down here that wasn't present before. So I'll give everyone a moment to figure out what this is. All right, well, that's been a moment. This is a arithmetic logic unit, or the ALU. And this is used in every single CPU, right? Not this exact ALU, right? There might be differences between my junky one and one that you would see in an actual like x86 architecture or whatever Apple uses. I don't know what they use for their chips. I can't think of it. x86 is the thing that like Intel uses. Probably C. This is just 1 bit. So this is a 1-bit ALU. So you can see there's quite a lot of circuitry for just 1 bit. What does our ALU provide us to do? Well, we obviously already know it lets us do math, right? It's in the name, arithmetic. So if we were to actually run the circuit, we can come over here and, well, click on... Alright everyone, I was having technical difficulties. I threw too many circuits inside of one of these simulators. It was having a meltdown. So, back to what I was saying. This is the ALU. Let's just look how it works, right? Well, we know it does math, right? Look, math, right? 1 plus 1 is 1, 0 in binary. And you got 1 plus 0 or 0 plus 1, right? We're getting the outputs we expect, right? There's also subtraction. You could check the truth table as I quickly go through this if you think, you know, to see if it's right. I'm pretty sure it is. I think I checked this a long time ago. This is actually an older circuit I made. And one of the things that spurred me on to actually make all these videos. Now, we know how that works, right? Now the real question is, how does certain sections of this work together, right? Well, if you see, there's the selectors that don't go anywhere, but normally in a CPU, you would see the control logic, which actually tells the ALU what operation is being performed. And so the operations are add, there's also usually a no op, meaning don't do anything. It depends on the architecture, right? But there can be a NAND, a NOR, or an exclusive OR for our case. And these are a bunch of different operations we can perform. And so the way we can perform these operations are by clicking our data select line and selecting a different data line. And so we have a NAND gate here. And so we have A and B, which A and B currently is 0, 0. So the NAND of 0 and 0, if you did them, would be 1. If you ever looked at the truth table for these gates, I don't know if I ever showed them. But we know how these gates work, right? So NAND of 0, 0, we get a 1. Or we can also change it to where we try to get the NOR of A and B, which is 0, 0, and the NOR is also 1, right? And of course, if we change this to 1, 0, you go for look at the NOR, right? Because we can see where the data line is currently selected. Selecting D2 or input 3. You can see that when we put 1 and 0 for A and B, and we select the NOR operation, the NOR operation travels to the multiplexer into the 4 input OR gate and out here, but in this case it's a 0, so there's nothing actually going that way. And then of course we can have the exclusive OR. You know, this is a little redundant because exclusive OR is actually pretty much identical to our exclusive OR gate here is the identical operation for addition. So we actually didn't need to put this in here. We could have used another gate, but we put it in anyway for some reason. And that's basically your ALU, right? So you have usually control logic that controls what is being selected over here. That control logic also decides what stage you're in for the CPU operation, whether it's the fetch, the decode, and execute steps, right? But that's for later. That's for later. But this is basically your ALU. Anyway, I could go into further detail, but I mean, this simple explanation should really just get the point across of what we're doing with this circuit and how it works, you know, functionally. Now, we can move on and look at the component level of this circuit, because I did build this at component level because something's wrong with me, I think. Okay, everyone. Now, it's a little laggy. I don't know why. I must have done something. But you can see this is our full, our arithmetic logic unit, 1-bit arithmetic logic unit at the component level. Now, it might be this multiplexer. We've seen this before, so we can delete this. And that might make it not run like crap. Now, if we take a look, right, we have our exclusive OR gate. We have a 3-input exclusive OR gate, which is made by using 2 exclusive OR gates. And then, of course, we have our AND gates and our OR, 3-input OR. We have our NAND gate. We have our NOR gate. And then we have our exclusive OR gate. So, you know, basically all the stuff we already saw in the last circuit, just at the component level, not at the abstracted level of the diagram. And this is what you would actually see in a CPU, right? You would see, probably not this logic type, you would either see maybe transistor logic or CMOS. I'm pretty sure you'd probably see CMOS over transistor logic. I could be wrong, like I said, this is new territory for me, really. Well, we can just take a look, right? So if we run the circuit, we have our A and B inputs, and then we have our add, subtract, selection, right? I don't know if I made this one wrong. I don't remember. This is the, I made 2 versions of this. One was wrong. I accidentally wired it incorrectly. I think this is the one that works. But let's say we add 1 and 1, right? So our carryout goes high, and our sum/difference is 0. So that's 1, 0. So we can see our addition works, right? 0 and 1, 1 and 0. Both give us a 1 output, right? Because 1 plus 0 is 1. And then our subtraction, so borrow out should be high. And then obviously we can take a look, maybe compare this to a truth table. It might not be 100% correct. I didn't check before recording this, but then we can also see our NAND and NOR gate. So if we go to the NAND and NOR gate, we can see the NOR operation. We can see the NAND operation. So this is high, high. This should be low. And then of course we can see our exclusive OR gate. You can see our exclusive OR gate is the exact same as our sum difference, as I said before. It's basically the same operation we're doing. So there's no need to include it, but we did anyway. You could have put any other type of gate, maybe like an OR gate or something. So we didn't actually need to include the exclusive OR gate, but it's there anyway now, so it's whatever. One thing I must note is that if this is not in the addition mode and it's in subtraction mode, well, our outputs for our NAND and NOR gate are going to be different than what they should be. And that's because if you saw in the full adder circuit, when we have this is high, it goes into exclusive OR gate. So as you might know, exclusive OR, it's one or the other. So we have one and not the other. And so this becomes high now, even though we don't have a B input. Anyway, this is the 1-bit ALU at the component level. So this is, as I said, a 1-bit ALU. So imagine the modern processor, right? A modern processor or CPU has like 64 of these per core, and let's say there's 10 cores, right? So you can imagine 640 of these all shoved onto a one board. Using CMOS logic instead of transistor logic or diode transistor logic. But they did build CPUs way back in the day using component level stuff. That's why they're all slow, and that's why the machine was actually massive, right? You always hear your teachers maybe say, back in my day, the computer used to take up an entire wall. And basically this is your ALU in a nutshell, right? I could have explained it more in depth, but this is just a general overview of most of these videos. I'm not your professor. They don't pay me to do that, so I'm not going to do it. Besides, reading the book, it can explain things, a million more things than I could. Besides, reading the book is good for you. Don't you know, like 54% of Americans can't read, like, proficiently? It's pretty sad. But anyway, yeah, that's your ALU, and I think it's a pretty cool circuit, and we'll see what else we can do with it.